Good morning, year 13s. How's it going, everybody? Right, last lesson of acid-base theory, and then you're on to your test. So today's lesson is on breaking buffers. Okay, it's nice to see everyone contribute on the chat. I'm just waiting for my YouTube video there you go. It's started. Hey, it's nice. There we go. So that's all running. I'll clear that now. Save myself the bandwidth. Right, okay, guys, I'm going to crack straight on with this. So share screen. Right, breaking buffers. Okay. Right, let's crack on. Last one. Title is breaking buffers. So this is A2. Oh, I'm going to switch to black. A2, acid-base. Acid-base, lesson 12. And the title is breaking buffers. Cool, I like it. All right, learning objectives. First one, I need you guys to understand the effect. Understand the effect of adding acid or base, acid stroke base on salt and weak acid in the buffer. I know it's a long learning objective. I apologize. I can actually just shortcut that. Acid-base effect on salt and weak acid. There you can do that. Next, know that buffers can only take so much, and then be able to calculate new pH. Right, 3 learning objectives. Okay, so before I start, because what we realize is acid base, we've done 12 lessons now on acid base, and they are done in a very, very, very distinct order. Yeah, very clear, distinct order. And the reason why is because in order to move to the next calculation, you need to be able to do the previous one. So it's reasonable for us to go back one and have a look at a question of, let's create a buffer first. This is what we did last lesson. So let's see how many of you guys can handle the question number 1. This is loud. This is me assessing your understanding from the previous lesson. Have you obtained it? Have you acquired it? Have you assimilated it? So question number 1. Ben mixes 200 centimeters cubed of sodium hydroxide. Concentration 0.3 moles per dm cubed. I'm just going to put molar. You know it's an old unit. You're not allowed to use it, but I am. Concentration 0.3 molar to 600 centimeters cubed. 600 centimeters cubed of yeah, let's stick with ethanoic. It's nice. Doesn't make any difference really. 600 centimeters cubed of ethanoic acid. Concentration. Let's do 0.23 molar. Right. Okay, guys. pH? Question mark. So first question I'd like to say to hopefully recognize is, I have not said in the question, and they do this about for half the time, I have not told you it's a buffer. You are expected to be able to read a question and recognize when it will be one. So how we recognize this is the fact that the base that Ben had chosen, he had chosen sodium hydroxide, 200 centimeters cubed, 0.3. And he's added it to a weak acid, but the weak acid is clearly thanks to the numbers, it's in clear excess. Yeah, this is in excess. What that means is this is going to be a buffer. Yeah, we recognize that this is method 2 for making. We talked about the 2 methods, one where you just add the salt and the other where you do a neutralization first. So everyone can run it. Everyone's probably already working on it already. Let's now run the answer. So answer to this question. First thing I'm going to do is I'm going to write down an equation because I think it's worthwhile. Just check to see whether or not it's a 1-to-1. And it is. This is good. Yeah. Sodium ethanoate plus water. And the equation is a 1-to-1 in regards. So 1-to-1 in regards to the weak acid and the base. Next step. Right, moles of acid. Let's do moles of base first. Since it was first in the question, let's do that. So first thing is number of moles equals C times V over 1,000 because I'm in centimeters cubed. If they gave me a liter, just be C times V. So it'll be decimeters. Right, on input my numbers, concentration is 0.3, volume is 200, and I over 1,000 on my calculator. I'd never do anything in my head in an exam. 0.3 times by 200 divided by 1,000, and I get 0.06 moles. Next, 1 mark. Can even have a mark for the equation as well. Next, moles of weak acid. Moles of weak acid. Already written down the equation there, so I'm not going to repeat that. So number of moles equals concentration, 0.23, times by a volume of 600, all over 1,000. Numbers, 0.23 multiplied by 600 divided by 1,000. And I get a moles of 0.138. So we realize that it is definitely in excess. Mark. Next. Right, now we need to run a neutralization. Excess acid. Yeah, so I'm now going to do 0.138. The ratio is a 1-to-1, so that makes things easier. Minus 0.06 equals minus, it's already on my calculator, 0.06. And I get 0.078 moles of weak acid in excess. I like it. Right, next one, my roadmap now appears. Yeah, my roadmap. Ka equals H plus, which is pH, salt concentration all over weak acid concentration. Right, so this now reminds me that I've got to convert each of them into concentration. It also, the key bit here is linking, recognizing that the moles of strong base are going to become the moles of salt. That is a key thing. So now I've recognized that, I now need to convert them all to their new concentrations. Okay, so I'm going to do it underneath, since I'm in that kind of general flow. So concentration of salt, I'll put salt concentration. Reorganize this equation. Yeah, number of moles times 1,000 over V, and it's the total V. Yeah, that's the trap. So my moles of salt is 0.06 multiplied by 1,000 all over the new total V of, I added 200 to 600, which is 800. So 0.06 multiplied by 1,000 divided by the total volume of 800 equals 0.075 moles per dm cubed. I like it. Next, concentration of weak acid. I've already written down the equation, don't need to do it. And I'm using the excess now, 0.078 times 1,000 over 800. 0.078 times 1,000 divided by 800 gives me 0.0975 moles per dm cubed. Now I insert these. I've suddenly realized I didn't give you a Ka value. I apologize. Ka at 1.7 times 10 to the minus 5. Apologies. What's the Ka? There's Dana. I can see exactly where she's up to. Right, now I can insert these numbers into my Ka roadmap and reorganize. Bring the weak acid over and the salt down. So I've got the weak acid, which is 0.0975 multiplied by, that's this bit here, which is the weak acid, and I'm bringing that one over to multiply it by the Ka, 1.7 times 10 to the minus 5. All over, there's my weak acid concentration. All over the salt concentration, which is 0.075, equals H plus. Run it through my calculator, 0.0975 times by 1.7 exponential minus 5 equals, divided by 0.075. I get an answer of 2.21 times 10 to the minus 5 minus log answer equals. And I get a pH of 4.66. And I'm done. Put your hand up if you got it. pH 4.66. The question didn't state number of decimal places, so I can just give it 3 sig fig. Can everyone give me a shout out on the chat if they got it, please? I like it. So that was the last lesson. How many people got it? Let's just have a quick wait on the chat. It's always nice because I'm using my sticky calculator still. Dat, did you get it? Come on, Dat. Give me a yay or nay. Dana got it. Excellent. Nikita got it. Yeah. Tenzi got it. Yeah. Amazing. 3 out of 3 so far. Ivan, thumbs up. Love it. Kayan, well done. Dat, well done. So I've got 6 people out of the class who are like, yeah, I'm on this. It's good. Emma, yeah, well done. Yup, well done, Ria. Yup, Emily, well done. Smiley face, love it. Josh, well done. It's a really good set. Well done, guys. Really pleased. If you're able to do this, these are the hardest calcs you'll ever do. But you see the process and why I've got this very distinct routine. Yeah? Gives you nice, easy, accessible marks. I like it. Right. Now we're going to break some buffers. Okay, title. Breaking buffers. Is that on the skinniest possible? No. Zoom in a bit more. Breaking buffers. Okay. So breaking buffers is it's not, by the way, I shouldn't really call it breaking buffers. I should call it changing buffers or using buffers or what happens to buffers, but I just prefer breaking buffers. It just sounds cooler. So we know that what we established in that previous question, we established an equilibrium between these two, our acid and its conjugate base. Yeah, and we can add the H plus there as well if we like, which is always quite nice to see it, but I do it in a different color. Yeah, but it's the equilibrium between these two. This is the acid, and this is the conjugate base. This is the CBAS. Yeah, they are related conjugates, so they don't play well together in a beaker. So we can set up an equilibrium and it acts as a buffer. So what now happens is we now need to look at this in terms of adding acid or base. Mr. Duncan, why is it ideal for the reagents to make buffers to be the same concentration? Is it so we know immediately which is an excess? Ria, well done, that's correct. That does tend to be a thing. They tend, in real exam questions, they tend to give you concentrations which are the same so that it becomes very obvious when it is a buffer. Yes, Ria, great question. I have to say is they don't have to. And what in reality, what you realize is the process you're running in this particular scenario is when you realize who's in excess, it actually tells you, you run the same steps no matter what the neutralization is. The fact that this results in a buffer is kind of seen in the numbers. Once you get to your moles, you know that this is going to be in excess, which means you then know to run the buffer steps after. Otherwise, you'd just run a normal weak acid or strong base pH calc at the end if the weak acid. Yeah, you get the point. So, okay. So where are these guys? So what we need to point out is, so if A, we add acid. Yeah, let's add acid. What would the impact be of us adding acid to this equilibrium? If we add an acid, yeah, so number one, if we add acid, number one, equilibrium goes that way, and the Seabass is reduced. The Seabass is reduced. The Seabass is going to get used up in that reaction if we add the acid because it's the conjugate base. Yeah? And therefore, as a result, number two, the weak acid will increase. One is reduced, one is increased. Now, what we can now do is look at this from a roadmap perspective. So if we now write out the Ka expression, what we can now see, salt, I'll do Seabass. Salt, the salt is the Seabass, yeah, over the weak acid. If we add acid in here, what's going to happen is the Seabass will drop, yeah, and the Seabass will drop and the weak acid will climb. I should have color-coded this. And the weak acid will climb. I could still color-code it. No idea how to do that. Weak acid, let's do it in orange. Yeah. Weak base can stay as a base. Blue's a weak base, I guess. You can stick with that. And then orange, so that one's going to do the exact opposite. It's going to climb. So what you realize is they're opposing each other. There you go. So one goes down, one goes up. So, okay, that's on addition of acid. What's going to happen then if I add a base to this? B. It's not big enough. The handwriting's getting bigger again. B. We add. What would happen if we added a base? Okay, number one, let's stick with the same routine. Number one, the conjugate base, the Seabass, yeah, if we add a base, what happens? If we add OH minus in here, yeah, the OH minus is going to react with the H plus. Oh, no, it's not. The H plus isn't there. That's not correct. The H plus is going to react with the acid. Yeah, it's going to react with that H there. It's going to rip it off. And it's going to push the equilibrium in the opposite direction. So number one, so this here is add acid, and this way is going to be add base. It's the opposite direction. So the Seabass would increase. Seabass would increase, and the weak acid would decrease. Let's look at it from a roadmap perspective. Ka, H plus is pH. Remember, it's basically not there at all in a buffer because the equilibrium is constantly absorbing it. Yeah, there's loads of conjugate base, remember. And then we've got the Seabass, the salt. You realize that linking all these things together is so important and understanding what each one of them is doing. Right, I've now added a base. Well, I just think about, I'm just like, hang on a second, if I add a base, yeah, if I add a base, I'm going to pull down the weak acid. I'm going to reduce it. It's going to react with it. It's going to destroy it. And therefore, I'm going to have an increase. Yeah, I should color code it. Yeah, and the Seabass would then increase. Once again, they're in opposites. This is important, guys. These little arrows here are so useful. I'd probably say just put those into your memory as best as you can. Yeah, if you add acid, they come together. If you add a base, they come apart. Yeah? I don't remember them like that, by the way. I simply remember if I add an acid, I'm going to reduce the base. Yeah, so if I've got one, then I've got the other. If I add a base, I'm going to reduce the acid, and I got the opposite for the weak conjugate base. Do you see what I'm doing? I have learned, I'm just going to show you what I have done. I have learned add acid. Add acid. Yeah, base drops. That's what I've learned. And then I've also said, well, hang on a minute. If that one drops, then the acid must increase. The arrows are opposites each other always in a buffer, in a breaking buffer question. I have learned add a base, then the acid will drop, and the other one must be in reverse. That's all I've remembered. Don't need the rest. Yeah, but the understanding is important. Okay, so now what we need to do is look at this from a question perspective. Okay, are you ready? Oh, question number 1. Okay, we've just made a buffer. We've got a buffer. There's another fact, by the way. I do want to add another nota bene here. Nota bene, before we go anywhere. Yeah, I'm going to add a quick nota bene here. And put that over there. Nota bene. If I add an acid to a buffer, the pH will drop by only a small amount. The key thing is, guys, what I need you guys to realize is it doesn't remain the same. It will, if you add an acid, it will become more acidic. It will drop. If you add a base, it will become more basic. The pH will increase, like it will. So we can predict it. Yeah, we can predict. If we add an acid, yeah, pH is probably going to drop by 0.1. If we add a base, it's probably going to increase by 0.1. Yeah, we can make these predictions. So let's have a look. So we've made, and the thing is, what we need to do is we need to use the question we've just done, because you're going to need that, guys. Okay. Okay. Zoom. Right. So in fact, the question, we'll put that in a bubble. The question needs to go here because we need all of this. This is everything we need for this question. Okay, guys, are you ready? Breaking buffers. Jasmine adds, because this is an extension of that previous question. Yeah? You can't break a buffer without having done a buffer already. Jasmine adds 10 centimeters cubed of 0.5 molar HCl to the buffer Ben created. pH? New pH, question mark? That's it. That is it, guys. That is the breaking buffer question. Okay, let's see how now we tackle this. So if I got given this question, the first thing I will do is draw a roadmap. Ka equals H plus salt, sea bass, over weak acid. Right, what I'm now going to do is I'm going to say, what did Jasmine add? Jasmine added an acid. The acid is going to pull down the salt. Yeah, I'm going to do that in a different color. The acid is going to pull down the salt because it's going to react with it because that's the sea bass. And therefore, it is going to increase the weak acid. Oh, okay. So now all we need to do is find out how many moles did she actually add. So, answer. Step 1. How many moles did Jasmine add? So, number of moles equals C times V over 1,000 because we're in centimeters cubed. Right, run my numbers in. Number of moles equals concentration, 0.5, times by a volume of 10, all over 1,000. So she's going to do 0.5, calculator on 0.5 times by 10, all over 1,000. Got to get to moles in chemistry. Times 10 to the minus 3 moles. Right, now I can use my roadmap. Yeah? And I'm going to go, salt's going to go down by that many moles. How many moles of salt were in the buffer originally? And the great thing is we already had it from our previous calculation. The moles of salt is there. We've already done it. We don't need to run it again. So we need to now say, right, we're going to do salt. So salt, I'm going to have, this is going to decrease. So I'm going to do this in, I shouldn't do it in black. Yeah, I'm going to do it in red, stick to red. Right, so salt, double dots. So we've got the moles of salt. We've got to switch, remember, you've got to remember to choose the moles. People forget and they use the concentration. You can't. You must go back in your calc. That's why, guys, if you don't show you're working, you are stuffed because you won't be able to find any of these numbers again and you'll have to run it all over again. You've got to be logical and show every process, labeling everything as you go. So I've got 0.06 moles of salt and I am going to remove, the HCl is going to reduce it. So I'm going to remove minus 5 times 10 to the minus 3. Right. So moles of salt after acid, 0.06 minus 5 exponential minus 3. So I now have 0.055 moles of salt left. Next, that's the salt, tick. Weak acid. Right, where's my weak acid moles? There they are. Yeah, gotta remember, I cannot use the concentration. Gotta go back to the moles in the solution. Now this one's going to be added, not subtracted. You see why the roadmap is so important? Holy moly. 0.078 plus 5 times 10 to the minus 3. It's the exact opposite. Right, 0.078 plus 5 exponential minus 3, calculator sticky, 0.083 moles of weak acid left. Right, shouldn't say left, it's now more. Right, guess what I've got to do now? Got to go back to concentration. Now I can go back to concentration. Got to get these to conc, both of them. Yeah, so I'm going to reorganize my equation. Yeah, we know it is number of moles equals C times V over 1,000. I'm now after concentration, reorganize. Moles times 1,000 over the new total V, which is 1,010. She added 10. No, it's not 1,010. It's 810. We had 800 centimeters cubed of the buffer. We now have a new volume because she added 10 centimeters cubed of acid. Let's now run each of these processes. So I've got this weak acid already on my calculator, times 1,000, divided by 810. So that becomes 0.102 moles per dm cubed, weak acid. Salt, 0.055 times 1,000 divided by 810 gives us 0.0679 moles per dm cubed. Now I input back into my roadmap and reorganize. Ka multiplied by the weak acid, the new weak acid divided by the new concentration of salt gives me H plus. The Ka value has not changed. Insert my numbers. So there's my weak acid. There's my salt. Input them into my calculator. So Ka 1.7 exponential minus 5 multiplied by the weak acid 0.102 equals divided by 0.0679 equals, and I get an output of this guy. I'm just going to write those in what I've just done. That's not big enough. 0.102 and 0.0679. And my output of that is 2.55 times 10 to the minus 5. Now, before I do anything, what was the pH of the buffer originally? And I've just added an acid. I'm looking for pH 4.55. Take it down by 0.1. What did I get? Let's find out. If it goes up, we're wrong. Minus log answer. Oh, it's always nerve-wracking. Acid bases equals 4.59. Nailed it. Yeah, look at that. Uh-oh. Uh-oh. Oh, no. No, 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 no. It's gone up. Oh, no. The pH has gone up, guys. Have I made a mistake? She added HCl. The pH should drop. There is more acid. The acid, have I gone and put them in the wrong places? What's the concentration of it? By the way, there is the occasional time when this does actually happen, but it's rather unusual. What I want to now compare is this picture here to this picture here. So the weak acid has definitely increased, and the weak base has definitely dropped. Interesting. It's become more basic. It's saying that the effect of the salt is greater than that of the weak acid. Huh. That's interesting. It tells us that they're massively, okay. Oh, isn't it lower than, oh, sorry, I'm an idiot. I was comparing it to my bloody number. God damn it, Mr. Duncan. Sorry, I shouldn't have said that. I apologize. It has dropped. I'm so sorry. Ignore me. There we go. There we go. It's done exactly what I said it would do. That's what I thought. Ignore me, guys. I was looking at my predicted. I'm an idiot. I shouldn't have written my predicted down. It's always a bad plan. It's done exactly what I thought it would do. Right. Okay, guys. Are you ready? Are you ready for the next one? Breaking buffers is hard. Right. Okay. Ugh. This is where I feel like we want to actually... okay. I ought to just grab real questions now. Question number 2. Ivan has 500 centimeters cubed, 500 centimeters cubed of a buffer. Oh, I'm tempted to make this really hard now. I'm going to make a mess of this if I do this. Problem is, if you start making up questions and I don't give you enough information, I'm going to stuff this up. Oh, I don't want to get lost and give you a question I can't answer. Ivan has a 500 centimeter cubed. Ivan has 500 centimeters cubed of a buffer. pH. I'm going to really stuff this up. 4.71. pH 4.71. Buffer contains, I'm taking a punt here, I really shouldn't do it. Buffer contains ethanoic acid. Ethanoic acid and sodium ethanoate. Sodium ethanoate. Sodium ethanoate. Ka, give you the Ka. Ka 1.7 times 10 to the minus 5. Question: what ratio of acid and salt exists in this buffer? Okay. Question mark. Okay, guys, this is for Dat. Dat, you're going to be able to support me here. So, guys, this is not a breaking buffer. It is a standard buffer question. This is just a standard making buffer. Yeah, even though you're not technically making one, which is entertaining, isn't it? So, guys, I want you to pause the video, have a go at doing this, and then and then unpause it to see if you get it right. I may get it wrong, we'll see. So, first things first, let's do a roadmap. Okay, I'm going to make my pen thicker. Answer. I always love a good challenge question. Answer. So, Ka equals H plus, that's the pH. Now, what's interesting is we've been given the pH. Yeah? Multiplied by the salt, or sea bass, all over the weak acid. Now, in terms of mathematics, one of the things that you can do here is you can actually separate out the H plus. So this equation can actually be represented like this. Ka equals H plus concentration multiplied by the salt concentration over the weak acid concentration. Mathematically, that is the same. I know it's all maths. Ask Dat to explain it to you sometime if you don't understand it. But you can actually just separate one of the top denominators out and just have the ratio of the other two. It's because you're still doing the same thing in terms of the fraction-wise. I don't know if that's the right words to say that. It's where my teaching of maths lets me down. But we can separate out that. Now, all they're looking for is the ratio. That there is the ratio. So all we actually need to do is just rearrange this. So if I simply move H plus over to the other side, we can also then say, or Ka divided, because we're going to divide everybody by H plus. Can you do that? I think that's right, yeah? Dat, just check me, over H plus will give me the salt, and weak acid ratio. Dat, am I correct so far, please? Is that the correct translation down to that? It is, right? Simple maths. Basic maths. I shouldn't say basic. No acid base. Right, so now that we've kind of followed our roadmap through here, what we can now do is we can first of all now translate the pH out. Second step, now that we've got to this 1 mark, we can now translate out pH. So to get from pH, yeah, we do 10 to the minus the pH. We did this when we were doing, we did this. We've done this various places in acid-base theory. Yeah, when we need to go from pH to concentration of H plus. So we can then say, therefore, 10 to the minus, and the pH was 4.71. So shift, turn my calculator on, shift log gives me the 10 picture, minus 4.71 equals. Right, so now that answer there is, so H plus concentration at that pH is 1.95 times 10 to the minus 5. I like it. We've got the Ka value, so all we now need to do is insert the two numbers in here. There's my H plus. My Ka was in the question. Let's just insert those. So we now get 1.7. I should write it like over here. Yeah, 1.7. Yeah, insert numbers. Yeah, 1.7 times 10 to the minus 5 over H plus, which is 1.95 times 10 to the minus 5 equals 1.7 exponential minus 5 divided by answer equals, and I get a ratio of 0.871. Now that's smaller. So what that means, if that's below 1, isn't that the equivalent of having it like that? That's the same, right? Is that the same? No, it's not. Oh, hang on a minute. That's then the number. So how do I then, hang on a sec. 0.871 equals, can I end it? No. If I do, that's the ratio. That number there equals the salt to weak acid. Yeah, that shows the ratio between those. Well, how could I split that into a fraction? If I do 1 over, so hang on, if I do 1 divided by, I do 1 divided by 0.871. Donna says no. That's hilarious. Donna says no, but Dad says yes. I get a value of 1.1, right. So what I've done is I've divided and it's smaller, so the bigger number needs to be on top. So now what I can do is I've divided 1 by that number, and it's given me, that little maths bit there gives me 1.148. Well, if I then do 1 over that, no, other way round, if I do 1 over 1.148, that should give me 1 divided by answer, gives me the same number. So the salt is 1, and then the bottom one, concentration is that. This is just the ratio, remember, it's not really the concentrations, it's just the ratio. It's 1 to 1.148. There's my answer. There's my ratio. It's just a ratio. Yeah, it's the same. Yeah, it's the same number, isn't it? Yeah, so if it's acid, isn't it 1 over... I just know that it's... that number needs to equal that one. I don't know. Have I got an extra step there that I don't need? I don't think it is just 1 over. I don't think it is, because if you do 1 over that value, it's not that value. Yeah, Donna, what you're saying, and this is weird, right? This is a bit of a maths game. Yeah, if you do equals, we know that it needs to be the salt to the acid. Yeah, salt over acid. Well, what we realize is that needs to equal, if we did 1 over 871, that doesn't give you that value. That there does not give you that value, which means it's not the same as it. Stop it with the silly maths games, please. Ivan, that divided, yeah, I think that actually does give that though, doesn't it? So that number divided by, but hang on. So hang on. Ivan's just said 0.871 over 1. Yeah, which gives us the same answer. Of course it is, divided by 1. Yeah, it's the same as. Same as. Yeah, that's fine. Right, now here's a question. Dad, now that we've got the ratio, this is the ratio, it's not the true concentrations. Considering we were given a volume in the question, 500 centimeters cubed, since we're given a volume, could we work out their concentrations as a result? We could, right? Because the concentrations are both, we can say, that we've gone that as that's the ratio, or that is concentration ratio. So number of moles equals C times V over 1,000. We've got V, but the V's are going to cancel. So are the thousands. Oh, I don't like it. We've got to put it into... can you work out the concentrations to give you that correct pH? Or are those actually the concentrations? No, you can't work out concentration. There you go. No, yeah. Anyway, fun games. I'm just playing games now. Anyway, so what I'm now going to do is, now that we've created this, is it possible, now that we've got our ratios of 0.871 over 1, is it possible to work out a new pH on addition of a base? Let's try, shall we? Is it possible? We should be able to, because we can treat them as legitimate concentrations. We can. Even if the concentrations aren't right, they will still increase or decrease proportionally. Is that right? Oh, yeah. Well, we can find out. So now that we've got all of that, oh, but we don't have moles. Oh no, we don't have moles. We've got concentration. You don't have moles. They're in the same volume. Could we treat them as moles? Dad, they're in the same volume. Can we treat them as moles? We can, right? We can use, because they're in the same volume of solution, it shouldn't, for what? Okay, all right. Question number 2. All right. Ivan adds 5 centimeters cubed of, how much did he have? He had 500. No, he could probably do more than that. 15 centimeters cubed of 0.2 molar sodium hydroxide. Yeah, new pH. New pH buffer. We know it's going to increase, but only by a tiny amount. So at this point, can we simply state, let's do moles of base. We've only got 3 minutes left. Now I'm going straight into another lesson. It's a disaster. I'm getting bigger and bigger and bigger and bigger and bigger. Moles of base. Number of moles is C times by V over 1,000. Can we just treat these directly 0.2? I don't think we can we? 0.2 times 15 over 1,000. Because that's going to give me 3 times 10 to the minus 3. Now, since the concentrations over here, we can't actually work out the moles of each one of them. We don't even know that, can we? Can only find their ratios. Can we not just treat that? So we've added sodium hydroxide. We know that in this roadmap, need my roadmap, Ka equals pH, H plus, over salt, all over weak acid. Right, he added a base. The base is going to pull down the acid. Yeah, it's going to pull down the acid. And it's going to increase the salt. Can we not treat the concentrations? Can't. You don't even know the concentration. But does it matter? We've got a ratio between them, and we know that the ratio is going to remain almost constant. Yeah, it shouldn't. Can we not just, I want to run it through just for fun. So just this might be complete garbage, guys. You can ignore me now at this point. You can all leave if you like. I don't care. So the salt is going to be moved up. So 0.71 plus 3 times 10 to the minus 3. 0.871 plus 3 exponential minus 3. It's nothing, 0.871. And then we've got a change in volume. That's a nightmare. Oh, no. Yeah, okay. Can't. It'll give us a rough pH change. Fun and games. Anyway, I'm just playing around. Guys, what I'm going to do, I'm going to leave it there today. You guys go to your next lesson. I'm late. I'm sorry, everyone. Guys, I hope you found it useful. I'll post some breaking buffer questions on the classroom for you to have a go at. And I will see you guys next lesson. So we're going to do one more lesson. One more lesson. Yeah, the test is not next lesson. I'm going to do one more of having a go at breaking buffers. And then your test is a week today. So just before Christmas. I'll see you guys later. Bye, guys.